This is the third lecture module on the topic of turbulence modeling, where we will present the k-epsilon and k-omega turbulence models. Let us look at the turbulent kinetic energy equation, which forms the heart of these turbulence models. Specifically, we will look at the mechanism of production of turbulence. To remind ourselves, turbulent kinetic energy is defined in terms of velocity fluctuations. And if you look at the simplest form of turbulent kinetic energy equation, we can write it or derive it from the momentum equation written for velocity fluctuations. We have done this before, and I'm going to do it again to recap. We have du prime dt plus u bar du prime dx plus u prime du bar dx plus some additional terms on the equal to minus 1 over rho dp prime dx, and then additional terms including sigma and tau, Reynolds stresses. We take this equation and what is called as take a moment of this equation with u prime, which means multiplying each term by u prime. The first term we had seen gives us the time derivative of turbulent kinetic energy. The second term gives us the mean convection effect. We will now look at the third term, which is of the form of u prime du bar dx. If I take it to the right hand side, it gets a form which is minus u prime square, same thing, du bar dx, the same thing with an additional minus sign on right hand side. Now u prime square is always positive because the square of a quantity, it could be a fluctuation which itself can be positive or negative, but square will always be positive. And if you look at scenarios when du bar dx is negative, mean velocity decreases with x. A simple scenario would be if the flow passes through a shock wave, the velocity of the flow, the mean velocity, goes from supersonic to subsonic, decreases, the derivative is negative. These two together will give you an overall positive effect, including the negative term. And this positive effect is called production or generation of turbulence, and it always happens because of gradient in mean velocity du bar dx. In fact, what we could do is to generalize this term on the right hand side, or production term, as tau 11 du bar dx, tau 11 being this quantity we have defined earlier, and then generalized one more level by saying tau ij du bar I dxj. So any velocity gradient, whether it's of u, v, or w in a general three-dimensional flow, in any of the directions, can generate turbulence, which is given by this form, and it is called, this is the term which appears in the turbulent kinetic energy equation, and it's called production. So to recap, we have discussed dissipation effect, diffusion effect, and now we have production effect. So if we combine all these things together, the full K equation, let's put it this way, full means in our own terms, that's all the terms are included. Final, maybe better word is final K equation after all the derivation is tk dt plus u bar j dk dxj convection equal to production, which is usually denoted as pk production minus epsilon, which is dissipation, plus nu times second derivative of k, which is diffusion, plus a similar diffusion effect comes because of turbulent mixing, which is denoted by nu t we have, which is the kinematic eddy viscosity replacing regular eddy viscosity, and the rest of the term has the same form. So this is called turbulent diffusion. So in the equation for turbulent kinetic energy, we have on the left hand side, it represents how turbulent kinetic energy accumulates at a point in the flow, which could be because of convection effect. Turbulence can be carried with the mean flow from another location to this point along a mean by the mean velocity. There could be generation of turbulence because of mean velocity gradients production. There could be dissipation because of friction effects, killing all those small fluctuations because they're rubbing against each other. And there can be diffusion, both molecular diffusion, which is kinematic viscosity, and turbulent diffusion because of eddy viscosity. So the key message here is that there are four mechanisms which can control turbulence, apart from convection, which is being carried by the flow, which is obviously there in any fluid mechanics phenomena. The four mechanisms are production, dissipation, diffusion, and turbulent mixing. Okay. We will now take this idea forward to write an equation for epsilon. If you look carefully, epsilon is the only unknown term in the K equation. So if we can find an equation for epsilon, then we can actually close the system and get all the terms required for turbulence modeling. So epsilon has a fairly complex definition, which we wrote in terms of derivatives of u prime xj, and we can actually derive an equation of similar to k, but it is way too complicated and people don't do it. Instead, they take what's called a phenomenological approach. They identify the different physical mechanisms, physical processes, physical phenomena which can affect turbulent dissipation rate epsilon, and write an equation of this form: d dt of epsilon plus u bar j d epsilon dxj equal to production of epsilon dissipation of epsilon, diffusion, molecular and turbulent diffusion of epsilon. Let me make it all these things of epsilon. So now, if we don't have an exact formula for production, dissipation, other quantities, an an alternate approach is to use what we know. We know that production of turbulence occurs because of mean velocity gradient. It has a form of what we have derived, shown as pk in terms of Reynolds stress and velocity gradients. If this is the production of k, a similar mechanism will generate epsilon, which is the second quantity which about turbulence, characterizing turbulence. So what's the simplest form of production that can be put into this equation that is dimensionally correct? That happens to be production of k times epsilon by k. So it divides by k and multiplies by epsilon to make it dimensionally correct for the epsilon equation. What about the dissipation term? In k equation we have dissipation as epsilon. We do the same thing, times epsilon by k. In fact, we get epsilon square by k. Naturally, they would not be the correct terms in the equation because they were not derived mathematically. So we would need some kind of a constant or some empirical functions in there to make it work, to give the right answer. So we get the production of epsilon has this form. The dissipation of epsilon has C2, and there's a negative sign. And again, C2 is an empirical constant parameter, or can also be a variable, a function of some other variable, plus nu plus nu t times diffusion, which is denoted by second derivative epsilon. So I will now simplify the equation by rearranging it a bit. I'm going to erase and clean up to make some space and write it in this form. So that we have finally an equation which we can use. Okay. Interesting. In fact, there are a few other empirical things thrown in, like there is something called sigma of epsilon, which is like another constant that is put in. There are sometimes functions, empirical functions also placed in these equations for them to give their answer, which will finally match experimental measurements in a boundary layer or some other kind of turbulent flow. Now, the important thing to note is that although the equation is not perfectly exact equation, it seems to work reasonably well. And it allows us to compute epsilon as a function of different locations in the flow in a CFD scenario, given the values of C1, C2, sigma, and all this kind of other constants that have been thrown in. So if we solve an equation for k and epsilon, along with the mean flow equations, there is a way to close this whole set of equations in which these two quantities actually determine the state of the turbulence, and they form what's called the k-epsilon turbulence model. Now, how do we use k and epsilon? We have seen the flavor of this before. We said the velocity scale of the turbulent motion, turbulent eddies, and whatever is happening, mixing happening in turbulence, is kind of proportional to square root of k, because k is the turbulent kinetic energy because of velocity fluctuations, and it gives you an estimate of how large the velocity fluctuations are. Dimensionally, it has to be a square root because to get the correct velocity scale, and the turbulent time scale T of turbulent is obtained as k over epsilon. Now, if you work out the units of k, which happens to be velocity squared, it's meter squared per second squared, and the units of epsilon are meter square per second cube. So essentially you would get some of these would cancel, and you would get second or a unit of time by doing this. Once again, this is more like a dimensional argument, and that there is a bit of physical analogy involved, which we will leave out as detailed. We can read up in the reference books and we can discuss separately. But the turbulent time scale, the turbulent eddies and vortices, if you think about what is the time they take to like maybe think about make one rotation, is approximately given by the turbulent time scale k by epsilon. If we know these two, then again by dimensional arguments we have, let me write that, dimensional arguments. Maybe I'll place it here, it's important for all of them. The turbulent length scale is velocity scale divided by, multiplied by time scale. Let's make some space here so that we can actually work our way through, times turbulent time scale, and it essentially gives us square root of k times k by, so it's k to the power of 3 halves by epsilon. So now using k and epsilon we get an estimate of the time or the length scale of the turbulent eddies. And if you now go back and remind ourselves that the eddy viscosity mu t is rho v turbulent L turbulent, it will be rho times v is square root of k, L is k to the power 3 halves, so it becomes k square by epsilon. In fact, we put a empirical constant there to make it an equality. So in a k epsilon turbulence model, we solve equations for k and epsilon which are of this kind. We get k and epsilon at every point, with which we now define the eddy viscosity at every point in the flow. And that eddy viscosity formula closes the set of equations, so we can actually compute all these variables without any unknown or unclosed term. Okay, let's go to the third part of the lecture module, where we extend this idea further to define what's called the k-omega turbulence model. Omega is defined as another variable which is epsilon by k. It has less of physical meaning, but it's actually a numerical trick to avoid numerical difficulties. It's actually numerically more robust than the epsilon equation if you write an equation for omega. The fact that in the epsilon equation, if you go back and see, there are many places it's 1 over k. If k goes to 0, for example in a laminar flow, you actually would end up with infinite values. So using omega helps us there. Now if we write the equation or form, we take the definition of mu t in terms of rho k and epsilon and change it to omega, we would actually get rho k by omega. And this also can be written as a kinematic form of eddy viscosity, which is k by omega. And and let's define it as kinematic eddy viscosity. Okay, we'll see how that comes into our help. The equation for omega has a very similar form, and once again it is not derived mathematically. You just write it in what's called phenomenological way. We identify the different phenomena which can create and destruct and diffuse any turbulence quantity, omega being another of such quantity. We would write production of K, which is again proportional to production of turbulence, which is or turbulent kinetic energy, times omega by K, which is the, make it correct dimensionally. This is actually written in terms of, I made a mistake. This is K by omega. So this becomes 1 over nu T, sorry, 1 over nu T times production of K. The other term is dissipation, which is epsilon, times omega by K, which again you can see easily is going to be omega times epsilon by K is another omega, so it's omega square. And we have to put in additional constants, which in this case has been called as beta 1 with a minus sign, and gamma 1 for the production term. And there are diffusion terms because of kinematic viscosity, molecular and turbulent, and there are additional empirical constants, del square omega del x j square. So then this becomes the omega equation, where gamma 1, beta 1, this are empirical parameters or constants. And if when we take omega equation of this form along with the K equation, and we are able to solve these two and then put the values of K and omega into the definition of eddy viscosity, we get what's called the k omega turbulence model. There are other variants of k epsilon and k omega turbulence models. There are also other kinds of turbulence models which solve slightly different form of equation. For example, they may solve for an equation, write a similar equation similar to this equation for eddy viscosity directly instead of k and omega, and so separate equations. There are many different kinds of turbulence models, but overall the ideas of turbulence modeling remain the same, that there are 4 mechanisms which can create or destruct or diffuse turbulence, and those are used in different ways to create equations, transport equations, differential equations that can be solved, just like the conservation equation for mass, momentum and energy. Okay, with this we will stop today's lecture and